Welcome to Part 4 in the module on patterns and frameworks for service configuration and activation. In previous parts of this module, we described the component configurator pattern, and we discussed the ACE service configurator framework that realizes this pattern in portable ways on many different operating system environments. We then discussed how to apply this particular pattern and the implementation in ACE to make our JAWS web server more configurable, more extensible, more dynamically changeable and assemblable at runtime. And now we're going to talk about another pattern that goes a little bit further to make it possible to be able to create server instances dynamically in response to incoming requests from clients. And this will be what's called the Activator pattern. We'll use the Activator pattern to further extend our pattern language for JAWS, so that not only are we going to use wrapper facade for portability, reactor for event handling, acceptor connector for connection establishment and service initialization, and component configurator for dynamically composing the implementations of our server, we're also going to be able to activate our server process on the fly when client requests come in. So let's first start by talking about the motivation for why we might want to use this pattern in the first place. The main reason for using this pattern is to try to minimize resource utilization. Imagine you're in an environment that's resource constrained. You don't have all the memory in the world. And it may also be somewhat dynamic. There may be periods of time when there's lots of requests. There may be other points of time where there's not a lot of requests for certain kinds of services. So keeping processes running all the time, even when they're not being accessed, may not be the most effective way of utilizing the resources. So how can we go about trying to make this work effectively? Well, one thing we might want to do is apply the Activator pattern in order to activate and deactivate server resources dynamically based on access patterns by clients. In our particular case, of course, we're focusing on activating and deactivating our JAWS web server processes, but in other cases, of course, it could be used for other examples as well. The Activator pattern automates scalable on-demand activation and deactivation of services that run in so-called service execution contexts, think process in this particular case, in order to run services that are accessed by many clients without consuming resources excessively. Another way to look at this from a structural point of view is we want to find some way to allow clients to activate servers to run services using an activator as an intermediary in order to get the job done, in order to start things up on demand. This particular pattern appears very briefly in the POSA 4 book. A longer version of the pattern can be found at the URL at this particular link, and it's appeared several other places, and this is the latest incarnation of describing this particular pattern. This is a dynamic view of how things work. Basically what happens is a client comes along and it invokes an operation that causes a request to be sent to a server, but rather than going directly to the server first, it's actually intercepted by an activator, and the activator checks to figure out how to run the service, and then it goes ahead typically and launches a server process and then passes the request along to the server process to carry out the work. You can do these things at various granularities. You can activate these things on each method call, on each transaction. You can keep them running for a while. There are different ways to go ahead and structure the particular dynamic activations of this approach. So let's talk about how we might apply the Activator pattern to the JAWS web server example. What we're going to do is we're going to leverage something called Inetd, which is a very common and popular Unix super server. There's actually implementations of Inetd for other platforms as well. Inetd supports two different kinds of services. Internal services that run in the Inetd process itself, and these include very short-lived services like echo or datetime. It also supports so-called external services. These are typically longer-running operations that run in separate processes that the Inetd super server will go ahead and fork and exec and do the appropriate socket bind, listen, accept calls in order to carry out getting these services connected to their clients. Examples of services that run this way would be things like FTP or secure FTP, Telnet or secure shells, or even HTTP web servers, as we're going to be doing here. Take a look at this link on Wikipedia to find out more information about what Inetd is and how it works. So let's talk about how this might actually play out in practice. So a client would go ahead and establish a connection on some server at whatever port number it thinks the web server is running at. Let's just use port 80 to make things more concrete. What would actually happen would be that the Inetd super server would be listening on that particular port. And it would do this because it would read a directive out of a configuration file called etc inetd-conf, and this configuration file will tell it to run a certain service at a particular port number and have a certain daemon process launchable when a connection request on that port comes in from a client. When a client goes ahead and connects to that port number, the Inetd super server will accept that connection, spawn the appropriate server process. In this case, it might be running the JAWS web server implementation. And then once that web server implementation is running, then when the client send the GET request to what they think is port 80, that is no longer being serviced by Inetd. It's now being serviced by the server that was spawned on demand by Inetd. So that server, of course, would receive the GET request, do the processing in ways we've seen before, and then send that result back to the client. The client doesn't really know this is being done by a super server. It just thinks it's being initiated and talking directly to the server the whole time, which is some of the powerful pieces of using this particular implementation of the Activator pattern. This design will use memory more efficiently because the server will only run when it's actually being accessed by a client. This makes sense, of course, if you don't have an environment where there is continual workload. If you had continual workload, you're probably better off just launching the server and keeping it running indefinitely, because there is some overhead to shut down and restart these server processes on demand every time a client request shows up. So let's talk about some of the benefits and limitations of this pattern. Some of the benefits, obviously, are the fact that we're not going to use resources unless we absolutely need them. We're not going to be allocating virtual memory. We're not going to be taking up slots in the process table. We're not going to be doing other things that would otherwise make the resource utilization higher if nobody's actually availing themselves of our resources that we're providing. Another benefit we get from this is we're able to get a nice, easy, coarse-grain concurrency model. What we basically get here is a process per request or a process per connection like approach. And that'll allow us to be able to get around some of the limitations we've talked about to this point by using the reactor pattern to have only one thread of control to process the requests from clients. Now we can have as many processes as there are clients that are sending us GET requests and making connections at any given point in time. You have to be careful there, of course, because you might end up having a lot of resources tied up that could be dealt better with other concurrency models like the thread pools we'll talk about later when we get to those sections. Modularity, testability, and reusability can also be improved by this approach because we're building our components out of more modular pieces where we can do them in isolation, we can test them, and then only when we're convinced that they're going to work properly do we go ahead and integrate them in to our actual environment. Needless to say, as with all different patterns and all different approaches, there are some limitations with this approach. So not unlike with component configurator, you don't necessarily know what's going to run until the requests start showing up from clients. And so there may be some determinism issues. It may take longer to start things up. You probably don't want to run an implementation of this pattern in a real-time system because things will take different amounts of time to run. The first time you run something may be different from the next time because it may still be running the next time. And that may be a problem for schedulability analysis and so on. Another problem, not unlike component configuration and the component configurator pattern, is what do you do about reliability or security? When you're starting to launch things dynamically, you have to be careful that people don't slip in Trojan horses that get launched that do malware or nefarious things to the state of your system while it's running. For that reason, by the way, people have begun to move away to some extent from using the Inetd approach in some environments where they can't have full trust and control over what's actually being run. And of course, another issue is just potential for increased runtime overhead and infrastructure complexity. There are more moving parts. There conceivably more things to go wrong. There's this additional latency for launching the servers on demand. The concurrency model we talked about process per connection, process per request, maybe heavier weight than you really want to use in practice. It turns out, as we've discussed here, that you can easily combine these patterns for service configuration and activation. So in this particular example here, we could use the activator pattern to bring in a server process on demand when a client connects, and we could also use the ACE service configuration framework in order to configure the state of the services running in that server when it's brought in and started dynamically. So this gives you a tremendous amount of flexibility and control over what kinds of things are running and when they run. And you just have to make sure you have a good grasp of the patterns, a good understanding of the frameworks, and a deep knowledge of the security implications and reliability implications to make sure these approaches work properly for the environments in which you run.